So we left off the last video saying Aylin's got some problems, and because Aylin's got some problems, sometimes we have to treat her a little special. Well, here's something pretty magical that Aylin can do. Aylin can be turned into a diazonium salt. This, on the right, this product, is a diazonium salt. Diazonium salts are weak electrophiles. They also have the world's greatest leaving group. Oh, click. My old boss used to say it that way. N2 is the world's greatest leaving group. That's nitrogen gas would be leaving. That's the major component of our atmosphere, the gas in most quantity in our atmosphere. Yeah, really great leaving group. Super stable molecule, N triple bond N stuff. The way it works is we add sodium nitrite. That's not nitrate, it's nitrite, and HCl, hydrochloric acid. Sure, I already started. These two things really do react together to form HNO2, which is nitrous acid. Nitric is HNO3, nitrous HNO2. That's what we're going to make. Nitrous acid could be the only thing written over the arrow, but it's often written as sodium nitrite and hydrochloric acid. Okay, how does the mechanism work? We said NaNO2. I usually like to make students draw this Lewis structure on their own because they struggle and realize, man, I forgot how to draw Lewis structures. That's the Lewis structure of nitrite. It's sodium nitrite. The sodium's a positive, so you got to have a negatively charged nitrite. That reacts with acid. We're going to make an electrophile like we did in our other electrophilic aromatic substitution reactions. This is not one of the big five, but we're going to make an electrophile similarly. This is nitrous acid. The acid I just told you we reacted to form. Nitrous acid gets protonated again because we're trying to make an electrophile. We protonate the one that already has an H. Why do we protonate the one that already has an H? Because when we've got a water like that, we can let it go, let it go. And usually we would say, let it go and leave behind a carbocation. This time we're leaving behind a nitrogen without an octet. That's not great. But that nitrogen without an octet has resonance. So this guy could become an N triple bond O. Dude, I'm really cracking up over here. N triple bond O with the oxygen with a positive. Among those two resonance pictures, which one's better? All day, every day, winter, chicken dinner over here, because everybody's got an octet. The nitrogen can handle the positive better than oxygen. It's true, but that's assuming that everybody has an octet. And right here, nitrogen does not have an octet, so be careful. Okay, so we're going to make an electrophile. That is our electrophile. In double bond O, that was our electrophile in nitration, and that's a nitronium. In triple bond O, or double bond with a positive nitrogen without octet, that's the nitrosonium ion. Yeah, I know, we got some crazy names in chemistry. I know. So this bit is formation of the electrophile, kind of like the electrophilic aromatic substitution we've been doing. I'm going to clear it so that I can continue my drawing on this same slide. And I need a lot of space. So if we start out with that N triple O with plus, and we're adding aniline. Aniline now attacks that electrophile. Only the nitrogen has a lone pair, and that's a better donor than the benzene's pi electrons, so nitrogen attacks the lone pair. Additionally, if you look back at what we're trying to make an N bonded to an N, so nitrogen attacks the nitrogen in order to hook up those two things. So we get this. Oxygen, we gave him extra electrons just there, so he's now neutral. Nitrogen got attacked. He had an octet before, if we put in our polka dots. He had an octet before. He's still got an octet now, that nitrogen does. this bottom nitrogen, the NH2 nitrogen, had no charge. Now he's making 4 bonds. He's got a plus. So if we analyze what we've got, what do we have that we don't want? HO. We've got a water connected to our stuff right now that we don't want. So we embark on a journey to get rid of water. So we can do a little intramolecular deprotonation right there to get an N with a lone pair back. N, you don't have to draw all these lone pairs, but I think it's helpful sometimes in this reaction to do so. We get an O with a plus. That's one step closer. Now this compound actually has resonance that is of importance because it helps us see what comes next. We get this thing double between the two N's and an OH over there, a plus on this nitrogen. Between those two compounds, which one's the winner chicken dinner? Which one contributes more to the hybrid? Both of them have an octet. Nitrogen with a plus is better than oxygen with a plus because it's less electronegative. So this bottom structure actually is the better one. We're still trying to make water, so let's do another deprotonation like that. If you look at other sources that have drawn this mechanism, like our textbook, for instance, they don't draw these steps intramolecularly. They draw them intermolecularly between, like, HCl in solution. So they would say some base comes to pick up this hydrogen, and then they would say this oxygen picks up an H from solution like HCl. It's my habit, mad habit probably, to draw it intramolecularly like this. Is it legitly intramolecular in solution? No, at least not the majority of the time. But acid-base reactions are very fast, and sometimes it is actually hard to measure whether it's an intra or intermolecular reaction. It's a long way for that thing to reach over there and grab that hydrogen, so it's probably not intramolecular, probably much more often intermolecular. Same deal here. This one is a little more realistic because they're closer together in solution, but it's probably a lot more often intermolecular in real life. But if you draw it as intra, that's okay to me, actually. Okay, this next reaction is not resonance. Back here it was, but this next reaction is a legit reaction. Lone pair folds down and kicks out that water. How do I know that one's not resonance? I broke a sigma bond. And if you go way back to our resonance rules, breaking a sigma bond is disallowed in resonance structures, so that's how I know this is not a resonance, it's an actual reaction. So I bust out water leaves, and I get my NN triple bond thing, my diazo, my diazonium salt. This is a salt because there's a positive. Who is the minus? It's most likely chloride because we added HCl, hydrochloric acid. That Cl minus is still hanging out in solution with my N triple bond N with a plus. Diazonium salts are weak electrophiles, so we will see them act as an electrophile. But they also contain the world's greatest leaving group, so we will see them leave as a leaving group as well. Because I drew this step intramolecularly, I skipped an intermediate. If some base had come to clean up the hydrogen on the nitrogen with a positive, and then we protonated the oxygen, we would go through an intermediate, this little green intermediate over here. It looks like this. This little green intermediate is a nitrosamine. Nitrosamines are intermediates that form when you have a primary amine that reacts, but it's also what happens when you have a secondary amine that reacts. This H would be an R group if you have a secondary amine. Why do I take a moment to talk about nitrosamines? Well, because nitrosamines, these processes lead to significant levels of nitrosamines in many foodstuffs, especially beer, fish, and fish byproducts. Also, meat and cheese products served with nitrite pickling salt The U.S. government established limits on the amount of nitrates used in meat products in order to decrease cancer risk in the population. Tobacco-specific nitrosamines can also be found in tobacco smoke, American dip, snuff, chewing tobacco, etc. So nitrosamines are things that form, this could be an R or an H, things that form when amines, primary and secondary amines, react with, I should probably put primary and secondary amines first, react with things like nitrite pickling salt, it's a food additive, and they come in contact with maybe our gastric juices or other source of acid. Nitrosamines are known carcinogens. So there are high levels of secondary and primary amines in some of these products, and when you add pickling salt or gastric juices or other sources of sodium nitrite and HCl, you end up with nitrosamines. Nitrosamines cause cancer. Not great news. Bacon has one of the highest levels, Bacon has one of the highest levels of nitrite pickling salt in all of the meats that are served, preserved meats especially. I still love me some bacon, even though it might cause me cancer. So it's not just aniline that can react with HNO2 and HCl to form a diazonium salt. Primary amines or other amines can also do that. So without drawing a full mechanism, because I just don't have space, and that's not the focus of this talk actually, without drawing a full mechanism, that amine over there can turn into a diazonium salt. You have to be a primary amine in order to turn into a diazonium salt. I don't know if I just said that wrong a minute ago. Sorry. These things form a carbocation. It spontaneously evolves nitrogen gas. What? And what kind of carbocation would make a primary? I told you, my old boss used to call into the world's greatest leaving group. It's so good at leaving, it can even leave behind a primary carbocation, even though that is traditionally a no-no. That thing would rearrange. Why would it rearrange? Because it could become a secondary carbocation. But furthermore, it becomes a resonance-stabilized secondary carbocation. Again, this is not the whole mechanism down here because it's not the point, but, well, that looks like, yeah, that's a 7-member ring. That's a resonance-stabilized carbocation like those vicinal diols, remember that? Yeah. So any primary amine could actually be turned into a diazonium salt and spontaneously evolve nitrogen gas. One problem with reactions that evolve gaseous products, if you keep them in a closed container and they try to evolve that gas, that container go boom. So we said diazonium salts can be electrophiles or they can act as a good leaving group. If you add a diazonium salt with a very activated benzene, like phenol, anisole, and anilines, you can get that diazonium salt to act as an electrophile. Why does it have to be a very activated benzene? Because this electrophile, number one, is weak, but you need to be able to do this reaction at low temperatures, and when you do a normal benzene reaction, you often have to put it under pretty extreme conditions, which often means heating, but this reaction cannot happen with heating because this guy cannot exist above about 0 degrees Celsius. So you need very activated benzenes. So what happens when you have a very activated benzene, this is your electrophile, so you attack said electrophile with benzene's pi electrons, and we would end up with this Wayland. Why did I stick it on the para position? Oh, that's not a triple anymore. Why did I stick it on the para position? Because that's a big benzene that you're connecting together. It should definitely go para. So if I use that pi bond to attack, my plus is over there. This is my Wayland. And all Waylands have resonance, and I could draw the resonance of this Wayland, but I'm not gonna. And then some base, somewhere, comes to take that hydrogen and restore aromaticity, and we get this thing. This really only happens with super activated benzenes because you need to be reacting at a low temperature. We get that thing. This thing reacts the same. If I put in pi bonds, I should not have left this as circles. We attack. Use benzene's pi electrons to attack said electrophile. We get this Wayland in methyl. Plus. Why might we attack the terminal nitrogen? Because if you attack the terminal nitrogen, you end up being able to take a hydrogen, restore aromaticity, and end up with a fully aromatic product. You have an aromatic ring up top and an aromatic ring on the bottom, and it's a totally neutral product. If you tried to attack the internal nitrogen, you would attack and fold electrons out to that nitrogen out there. It actually would leave this nitrogen that's internal still with a positive charge, and it would put a negative charge on that terminal one, and there's no way you can satisfy those charges. So it's much better to attack the terminal and give electrons to that internal, and then everybody gets satisfied, no more charges. Yeah? What's super cool, magical about compounds like these, this final product and that final product, is they have a ton of conjugated pi electrons. And things that have a ton of conjugated pi electrons have a long lambda max. What? A long lambda max in a UV visible spectroscopy thing. Visible. They would have a long lambda max, a long wavelength of absorbance. And if that wavelength of absorbance comes between approximately 400 and 700 nanometers, maybe this is getting familiar, I don't know. If that comes between 400 and 700 nanometers, they often appear as colored compounds. So these kinds of compounds are called azo dyes. Because azo dyes have lots of conjugation, they appear as colored compounds. That red circled bit is called an azo linkage. It's an A. Azo. So, why did I pick out this one? Because it's orange. Yeah, this specific one is orange. What kind of questions might I ask you about dyes like this? Well, I could ask you, what two pieces did this dye come from? What diazonium compound and other compound did this dye come from? What I'm really having to decide is, did this part used to be the N triple bond N diazonium, or did this part used to be the N triple bond N diazonium? The way I know that is the other half of the molecule. Remember, diazoniums are weak electrophiles. They have to react with super activated benzenes. So I want to split it so that the diazonium is on the less activated ring, leaving the more activated ring to react with the diazonium. Yeah? What that really means is this thing with the sulfonic acid on it has to have been my diazonium, and my aniline, that's not regular aniline, it's in dimethyl aniline. My aniline has to have reacted with it to create that dye. So you should expect to be asked, expect to answer questions about, here's a dye, what two compounds came together to make it? When I ask you to synthesize a dye like this, I'm not asking you to go all the way back and make these from benzenes, although I might, but I'm not generally asking you to do that. Okay. One reason that azo dyes are also cool and important, they're food additives. Have you ever thought about why Doritos are orange? Because that powdered cheese is orange. That's the dye that makes that powdered cheese so orange. That's the dye that makes that Mountain Dew yellow. Tartrazine is an azo dye. It's called yellow number 5. Maybe you've heard of it. It's found in many products, including confectionery, cotton candy, soft drinks, energy drinks, instant puddings, flavored corn chips, cereals, cake mixes, pastries, custard powder, soups, particularly instant cube soups, sauces, some rices, powdered sports drinks, powdered drink mixes, sports drinks, ice cream, ice pops, candy, peach, marshmallow treats, chewing gum, marzipan, jelly gelatins, jam jelly gelatins, marmalade, mustard, horseradish, yogurt, noodles such as egg noodles and Kraft Dinner, pickles and other pickled products, certain brands of fruit squash, fruit cordial, potato chips, Biscuits, caviar, wine, beer mixers, and many convenience foods together with glycerin, lemon, and honey products. It is even fed to chickens to make their yolks of their eggs appear more yellow and nutritious. Isn't that kind of a little bit crazy? Yeah. You know, something else that we've discovered? Some of these food dyes and azo dyes are carcinogenic. Yeah, today is the cancer lecture. So we said diazoniums are weak electrophiles and they can react with super activated benzenes to make things like those azo dyes. They can also, they also do contain the world's greatest leaving group, so they can be displaced. The NN can be displaced and something else can take its place. Well, maybe cool news for you is we won't walk through the mechanism of any of these reactions because the mechanism of many of these reactions is not well understood. Some of them are believed to involve radicals. Some of them are believed to involve aryl carbocations. Yeah, aryl carbocations. So we're not drawing any mechanisms for these. We're just knowing that these things can displace that N triple bond N and replace it with these other groups. One thing of note, this is potassium iodide. That's just regular plain I-. But this has to be copper chloride and it has to be copper cyanide, as in it cannot be sodium cyanide. It cannot be potassium chloride because those two that involve copper, we have pretty good evidence that those go through a radical and the copper is necessary in order for that radical to form properly. So yeah, copper is needed for those two, but potassium iodide works just fine. Now, this one over here with water, what do you suppose might displace that? You can make phenol out of that thing. There are several reagents that can be added here to make phenol. Copper to oxide is one of them. It often has water as well, but yeah, hydroxide itself I've seen just listed as a thing that can displace this. So sometimes students get a little creative with these things and just throw in all kinds of stuff and expect it to displace. Well, there are limitations on it, but yeah. This guy is fluoroboric acid. It's actually an H plus and a BF4 minus. Yeah. In all these others, I didn't point it out, but you're looking for a nucleophile to take the place of the diazo, to take the place of the N triple bond N. In this one, it's F that takes the place of it. And F minus is ejected from that boron and takes the place of the N2. This one says, watch out. This is hypophosphorus acid. Hypophosphorus acid replaces the N2 with a hydrogen. And you might say, why is that useful whatsoever? Well, let me show you why that might be useful. After step 1 here, we have a nitro group connected. After step 2, this should really have hydroxide, because if you don't add hydroxide, you're going to get an anilinium, an NH3 with a plus, but if you add hydroxide, you get an NH2. If you add Br2 with no catalyst, why is it important to have no catalyst? See the end of the previous video. You get NH2 with 3 Brs on there. What? This turns NH2 into an N triple bond N into a diazonium salt. And then finally, hypophosphorus acid gets rid of that diazo, replaces it with a hydrogen. We end up with 1,3,5-tribromobenzene. 1,3,5-tribromobenzene. Could you imagine another way to make 1,3,5-tribromobenzene? No. There's not really another way to make them because bromines are orthoparadirectors, and you're wanting all three of them to be meta to each other. So you do this kind of weird, kind of unconventional route, but you get the right product. Next, if we start with SO3 and H2SO4, we get a sulfonic acid on there. Sulfonic acid. HNO3H2SO4, that puts on a nitro group meta to my sulfonic acid. Superheated steam, that takes away my sulfonic acid. Iron and HCl, and one of these days I'm going to remember to edit that and add hydroxide. One day. Not today, obviously. I reduce my nitro in O2 to an H2. NaNO2 and HCl, sodium nitrite, HCl. HNO2 does the same dang thing. Make it a diazonium salt. And then take it away. And right about now, I guess you're probably thinking, why the heck did we do that? It was just a flex. That's all. Just to prove that we can. We know how to put a sulfonic acid on. We know how to take it off. Now we know how to put a nitro group on and take it off. It's a lot more steps, though, than taking off sulfonic acid. But we can do it. We can flex like that. That's all right. All right. That's good. Goodbye.